Okay, so let's first talk about classical mechanics. Okay, so let's say we have a particle and let's name it A, and it's moving around, right? We can describe its motion using the equation mass times second derivative of position with respect to time equals force, and this is Newton's second law. When we solve this differential equation, we get x of t, the motion or path of the particle. Okay. That's classical mechanics. In quantum mechanics, it's quite different. Instead of now talking about differential equations that, when solved, give us the path of the particle, we talk about differential equations that, when we solve it, it gives us the probability density of the particle. Now that might seem a little bit strange, but basically, the probability density of the particle tells us the probability that we find a particle if we test to try to find where it is. It gives us the probability that we find it in a certain x at a certain time. Okay, so that probability density function is governed by this equation, and it is called Schrodinger's equation. Okay, so I'm gonna write it down here. Okay, so first of all, I is the square root of -1. H bar is the reduced Planck's constant, so it's the original Planck's constant divided by 2 pi, and we differentiate the original Planck's constant with the reduced Planck's constant by labeling the reduced Planck's constant with a bar on the H. Okay, mass m here is just the mass, and then these are obviously partial derivatives, and v is the potential function of the system. Okay, so this is Schrodinger's equation. Now, when we solve this, it gives us the function x, psi of x of t. Okay, and what we say is that when we take the norm squared of this function, that gives us the probability density function. Okay, this norm, obviously, since it's a complex function, will be given by the complex conjugate times the original function. Okay, that will be equal to that. Okay, so for example, our wave function might look something like this. Wait, sorry, let me just label this as psi. My bad. Well, it might look something like this, okay? This is just completely arbitrary. So let's say we want to find the probability that if we look for the particle using our lab equipment, let's say, we want to find the probability that it's in between x equals -4 and -3, just for example, okay? So what we do is we take this psi and we take the norm of it, right? Which is the complex conjugate times the original function, as I just said. So the amplitude will be squared here, and we get the probability density function, right? So if we square this wave function, it might look something like that. Well, I'm just really bad at drawing, but anyway. And then after that, we can take the area under the curve between -4 and -3 to find the total probability that we'll find it somewhere in that region. Now, of course, this is only valid for a certain time t0, okay? Because if we let our time evolve from t0 to some other time t, then the wave function might look much different from this, and we might not get the same probability of finding it from -4 to -3 because it might have moved away or something. Okay, so anyway, that's the basic idea. The wave function squared basically gives us the probability density, and the probability density gives us the probability of finding that particle in a certain region in space at a given time. That's the main idea that is important in quantum mechanics. Okay. Okay, so this is of course a partial differential equation, right? We have some techniques of solving this, so let's apply that. Okay, so this psi is a function of x and t, space and time. Okay, now if you recall one of the techniques we have for solving these types of equations, which is called separation of variables, if it's a partial differential equation and the function is a function of more than one variables, right? We can say that instead of having this entire function being a function of two variables here, the psi of x and t, we can say it's the product of two other functions that are functions of the independent variables of psi, right? So we basically split it up and say, let's guess that we can write psi of x and t as the product of two other functions, x of x and t of t, so that we have now split up the variables into independent functions, and we no longer have to deal with the multivariable function, which makes life a little bit easier, as you'll see in a bit. So next thing we do, we replace the size of t's here, and the size in this Schrodinger equation, with our guess. Okay. Okay, so now we have x of x, t of t, differentiated with respect to time, equals negative h bar divided by 2m of second derivative of x of x, t of t, with respect to position, plus v times x of x and t of t. Okay, so I'm running out of space there, but whatever. Now, this derivative with respect to time only acts obviously on the time variable, so we can bring this x outside of the derivative like it's a constant. So this becomes ihx. Now I'm going to start writing the x of x, and I'm going to start writing the variables for the given functions because it should be obvious. Right, so we brought it out because it acts like a constant under the partial derivative, and we'll do the same on this right hand side. So we bring out the t because this is only a derivative with respect to x, right? There's no x in this function, so we can bring it out. Okay, so the recording actually crashed there, so I was in the middle of writing this equation down, so I'm just going to continue writing it. Okay, so we just recently brought out the t. Now I just rewrite the rest of the equation. Okay, v, x, and t. Okay. Okay. Now to simplify this a little bit more, we can divide both sides by x times t, the functions x times t. Okay, so this will cancel. This will cancel, and then these two will get cancelled out also. So we're going to be left with this after we after we do our cancellations. Okay, so let's notice something here. This right hand side is a function only of x, right? Because these capital X's here are functions of x, and there's no other variable in this right hand side except for x, so this is a function only of x, this right hand side. This left hand side is a function only of t, right? There's no x dependence here, nor is there any other variable, so this is a function only of t. So how can a function of time, completely of time, be equal to a function completely of x? There's no way, unless they're both constants. Okay? So the next step that we do in this separation of variables technique is we take this side we take this side and we set it equal to a constant, and we take this side, we set it equal to another constant, and we get two separate equations. So let's do that. And the other side of the equation is this. Wait, there's supposed to be a 1 over x here. Equals c. Okay, so notice that for the most part of this video, we've only been following very closely the method given to us by separation of variables. Okay, so we're not doing any physics yet. Okay, just keep that in mind. All of this have basically been just the outlining of a method. So don't get too confused over why we're doing certain things. It's part of the method. Okay, so now we have these two independent equations. These actually have names. This one's called the time-dependent Schrodinger equation for obvious reasons. It's a function only of time. And this one's called the time-independent Schrodinger equation. Okay, so now we're going to do something else, right? So we set these two equations equal to c, right? We can choose the form of c as long as it's still equal to some constant. We're going to actually choose the form of c to be E, energy. See why in a second here. Okay, so let's now, with our variables separated into two separate equations, we can solve each of them. So we can solve this first one. It's quite easy to solve the time-dependent Schrodinger equation. We can solve this one quite fast. So we're going to multiply both sides by the function t, and we get this. Then we multiply both sides by the exponential, not the exponential, sorry, my bad, but we multiply both sides by I and divide both sides by h, and then we should get the next part of our equation, which is this, I over h bar te. And then we just divide both sides by -1 to transfer this negative sign, or multiply both sides by -1, it doesn't really matter. Now there's a negative sign on the right hand side. Okay, I'm gonna actually write the e over here as well. Okay, so this equation can be solved quite easily. The solution is given by this, e to the -I e t over h bar. Now you can see this. You can see why our solution is an exponential quite obviously, because, well, we're taking the derivative of some function and we're getting that function back, but with this other factor out here in front, the -I e over h bar. So that's very telltale signs of an exponential solution. Anyway, let's turn our eyes towards this other equation, the time-independent Schrodinger equation. Okay, so we multiply again both sides by the function x, like we did in the time-dependent Schrodinger equation, and we should get this equals ex. Make sure you don't get confused by the capital X's and the x's. Remember that this x is a variable while this one's a function. Okay, so after we get this, we realize that this potential function, which is a function v of x that describes our system, we can't actually progress any much. We can't actually gain any more progression with this equation until we know the form of our potential function, right? Because at this point we're just solving for two unknowns. We're solving for v and we're solving for the function x. We can't do that with only one equation. So we actually can't go much further than this, and we'll say this is our most simplified form for now. When we do start doing word problems and actual physics, we can plug in the situation or the system into this v, So this v is kind of like where the unique solutions of the Schrodinger equation come from, because for each individual system we were gonna get a new solution basically. Yeah, so it's basically where we plug in our environment. Think of it that way. That's how I like to think of it. We're given a word problem, we discern the environment based on that word problem, and we plug it into V. Okay, then we just solve the equation, which we can now because we know V. Okay, so the last thing I'm going to do is I'm going to rewrite this equation, and instead of using a capital X to denote x of x, I'm going to use psi. Okay, so this might be confusing, but this is purely notational, I assure you. It's basically notation to write the time-independent Schrodinger equation with a psi rather than an x, and we should get this. Okay. Now note that this psi, it's a psi only of x, right? Whereas in the original Schrodinger equation, we got a psi of x and t. Now make sure that you don't confuse both of them. One of them is the full solution, the other one's just half of the solution, because we still don't have the time dependence on this solution, right? Okay, so the last thing I'll talk about for this video is how to construct the full solution, psi of x and t, given our solution for the time independent Schrodinger equation, x of x, okay, or psi of x, using our new notation. So remember that our guess was that psi of x and t can be written as the product of two other functions, x of x and t of t, and our x of x is given by the time independent Schrodinger equation, right? So once we solve it, the time independent equation, all we have to do is we get that function that we just solved for, and we plug it in to this x of x here, right? So we'll get psi of x, and then we multiply it onto it the solution for the time dependent Schrodinger equation, which was, remember, it was this. So that's e to the negative I e t over h bar, and that will be your full solution for that given potential. That's all.